Imagine a world where solar panels never lose efficiency due to unnoticed faults. This groundbreaking technology could make it a reality. An international research team has developed a novel PV fault detection method based on deep learning of aerial images. The proposed methodology utilizes the convolutional neural network (CNN) architecture UNet for image segmentation and then applies the CNN architecture Inception 3 net for fault classification. The presence of dust, snow, bird droppings, and other physical and electrical problems on the surfaces of the solar panels may lead to energy losses, the academics said. The need for efficient monitoring and cleansing protocols in solar energy systems cannot be emphasized enough. Based on that purpose, we have selected research subjects to enhance the image processing and classification tasks related to various types of damage to solar panels. For the model's segmentation step, the group used a publicly available annotated database of 4,616 images. The aerial pictures were divided into 6 categories: ground cropland, grassland, saline alkali, shrubwood, water surface, and rooftop. The database was split in a 60%, 20%, 20% ratio for training, validation, and testing, respectively. A different database containing 885 images was split in the same ratio for fault classification. The dataset comprises 6 categories of PV issues: clean, dusty, birds drop, electrical damage, physical damage, and snow covered. Aside from the Inception 3 net model, which applies the Inception 3 base with image net weights, the researchers also tested other classification models for compression. Those were DenseNet, MobileNet 3, VGG19, CNN, VGG16, ResNet 50 and Inception 3. Initially, aerial satellite images are processed using the UNet model architecture with a 256 by 256 by 3 input shape, undergoing 3 stages: decoding the input, combining encoding and decoding, and generating the output, the group explained. It also stressed that the Inception 3 net architecture uses the Inception 3 base with image net weights, enhanced by convolutional layers, squeeze and excitation, SE, blocks, residual connections, and global average pooling. The model includes 2 dense layers with leaky ReLU and batch normalization, ending with a softmax output layer. It also utilizes data augmentation techniques such as rotation, shift, shear, zoom, and brightness adjustments. The model is trained using the Atom Optimizer with a learning rate of 0.0001 and categorical cross-entropy loss, they also said. Their analysis showed that the proposed Inception 3 net achieved validation accuracy of 98.34% and an F1 score, which represents the balance between precision and recall, of 0.99%. That is compared with validation accuracy in the range of 20.9%, 89.87% and F1 of 0.21 to 0.92 in the competing models. The testing results also showed that the proposed Inception 3 net achieved a validation accuracy of 94.35% and an F1 score of 0.94. This is compared with validation accuracy in the range of 21%, 90.19% and F1 of 0.19 to 0.91 in the competing models. Future work could address several open scopes to further improvement in the Inception 3 net model's capabilities, concluded the researchers. Applying the model to other renewable energy systems, such as wind turbines or hydroelectric plants, would test its versatility. Further optimization of the model for real-time fault detection could be outlined as future work to improve its practical utility. The novel method was presented in SPF-Net, Solar Panel Fault Detection Using UNet-Based Deep Learning Image Classification, published in Energy Reports. The team included scientists from Bangladesh's American International University Bangladesh, Saudi Arabia's King Saud University, and India's GMR Institute of Technology have conducted the study.